So this is where we left last time. So this would be the third part of the presentation on chapter one. And last time we were talking about uh, semiconductor technology and how it's become much more complex um, per cost unit. And we were saying that well, the main driver of that is that the raw material for semiconductors is very inexpensive. Essentially, silicon that comes from sand. So now, just a little bit of you can have a course on semiconductors, but basically, you take a neutral material like silicon that has four electrons on the other band, and basically you dope it with some other material that can donate an electron, so it would make it like n-type, or it will uh, sort of steal an electron and it will make it p-type. So you dope it with these ions, sort of like you know barium or boron or phosphorus, something that is close, but it's not quite on the same column of the periodic table. It's either on the left or the right, and then you can get materials that are N or P type semiconductors, and that's where the whole technology comes from. Now, just to give you an idea, the whole process is very interesting. I said that the raw material is inexpensive. The process itself is very complex, very expensive, but you do get very easily economies of scale because you can have what is called wafers and have multiple chips fabricated at the same time. And these wafers can be easily 30 centimeters in diameter. So that's, like this big. And so you can get a lot of chips on a single wafer, and that adds to the economies of scale. What makes it challenging is actually the trend of having more devices and making the devices smaller. That makes it challenging because the process is sort of a lithographic process. So as the geometries get smaller, you cannot even use regular optics anymore for visible light. You have to use ultraviolet, and that's not even enough. Ultraviolet is too big of a wavelength for the sizes and geometries that we're talking about. So you have to use phase shift lithography based on ultraviolet that relies on the differential sizes of the wavelength. So it's very complex. But just to give you an idea, you get silicon. Now, the one thing about this silicon is that it is a single lattice. So it basically is the lattice is a single crystal in the lattice. And very few dislocations or intrinsic imperfections. So from the sand you get this pure silicon, sort of it's called an ingot, but it's really like a rod, a rod that is the diameter of the wafer. So if the diameter of the wafer is 30 centimeters, that's how wide the rod is. And then you slice it with a laser, and you get blank wafers, okay? And all these 20 to 40 processing steps, that's what is challenging and advanced. And it has to be done because of the dimensions and the geometries. You cannot have any type of impurity or any type of pollution, essentially. So this fabrication is done in very high class, what is called clean rooms, and they can be anytime from 10, just to give you an idea, from 10 to 100 times cleaner in the sense of the lack of particles than an operating room. So much more cleaner than an operating room, and that's where this 20 to 40 processing steps that takes place on top of that wafer and also below the surface of the silicon wafer uh, gets done, and you get your chips. Okay, and they get tested at the wafer level, and the ones that don't pass the test, they get probed. Uh, the chips will have pads, and there are probers that come down with needles and probe, and they mark with ink the bad chips. You're always going to have bad chips. Why? Because you will never have a zero defect pure single crystal silicon. There's always going to be some level of intrinsic defects, and if there are intrinsic defects, then uh, the semiconductor technology is not going to work, and there is nothing you can do about that. That's just a function of the raw material and a function of the material itself. But so the ones that are good, after you dice, you basically cut the chips up and down, left and right. You basically put it in a package, okay? And there are, packaging itself can be very sophisticated depending on the application. There are multiple cavity packages where you can put multiple chips on this on a single package. For example, one of the a few years ago, one of the Pentium chips, it was a two cavity package where they had the main processor in one cavity and they have the level 2 cache on the other cavity, but in the same package to minimize the delay of the electrical signaling between the dies. So after they are in the package, they get tested again, and you may lose some, but at this point the yield is very high. So it's usually the yield after you put it in the package, since you did a testing at the wafer level, is almost 100%. However, the yield at the wafer level, that's the first test that you do, can vary. It could be 60%, could be 70%, 80%. You're going to lose quite a few due to the intrinsic defects in the material. And that yield is proportional to the size, because if the chip is larger, then statistically you have more of a chance of having intrinsic defects that are in a place on the chip that is going to kill the functionality. So this is the size of a wafer. So 300 millimeter wafer. So this is exactly 30 centimeters, and you can see all the chips pattern. It has 280 chips just on one wafer. This is at a critical dimension of 32 nanometers, and each chip is about 2 by 1 centimeter. You can see that it's kind of rectangular. Okay. So the cost is very important. So obviously the cost per die is the cost of the wafer divided by the dies per wafer times the yield, which is less than 1. So and then the dies per the wafer is proportional to the area of the wafer divided by the area of the die. So you want to take advantage of the economies of scale. You want to have dies per wafer be as large as possible. So this number comes down. To get this as large as possible, you want the wafer area to be as big as possible, and you want to minimize. You want the die area to be as small as possible. So minimizing the area of the chip is very important. Then the other thing that you want to do here is you want to maximize your yield. So you want this, ideally it would be great if it was 1, but the yield is dependent on that expression, that third expression, which is nonlinear, and it's 1 plus the defects per area. So that is the intrinsic defect density of the raw material or the wafer that you are working with, times the die area divided by 2, all that square. Okay, so in here, if you want to increase the yield, the only thing you can do is make your die area smaller. So that's, again, that's why making overall in the cost per die, which is so important, the minimizing the die area is so important. Okay, so now we're going to start discussing performance of computing systems. So I wanted to start with this, 4 graphs of data of obviously a complex system. They are airplanes. And in the top, um, in the top to the left, we have a comparison of 4 airplanes according to passenger capacity. Then we have the same thing, the next one to the right, we have cruising range. Okay, so how far can it go without having to refuel? Then we have the cruising speed at the bottom on the left. And then finally, we have the number of passengers times the cruising speed as a metric in that bottom right corner. So we have 4 different metrics. We are comparing 4 different systems. They all do the same thing basically. And then if the question was, which one is the best? That's a valid question. Well, I can tell you that the answer doesn't come about immediately just by looking at the data. You have to add more information. You have to add, when you ask the question which one is the best, you have to tell people what is the intent, what is the application. Because, so the answer is it depends. Without knowing more, without knowing what the end usage is going to be, in this case for an airplane, for an airline would be the business model that airplane is going to be intended for, you don't have enough information. So the answer would be it depends. Because if you were doing very long haul flights, for example, if you were trying to fly from Dallas to Japan, probably cruising range is very important. You don't want to have to drop down in Hawaii for refueling. So that may be very important. If you were trying to set up a leg where it was relatively short trips, then the cruising range doesn't matter. And if the business warranted to have many trips per day, probably the cruising speed would be most important. Or if you were trying to have a leg where 1 flight a day and minimize the number of flights per day, then the passenger capacity may be the most important thing. So what we're going to see is that when we design these processor chips, we have to keep in mind what is the intended application and the use case as we try to design for performance. But when we measure performance, it has to be in the context of the usage. That's the intent of this chart. Okay. So we're going to talk about how to evaluate performance in processors and computer systems, so we can compare because architecting and designing chip architecture is looking at the different possibilities, different hows of how we can do something, achieve the architecture of a chip, and then being able to compare which is the best one, which is the best performance in the context of the usage and the business case. So that's why knowing how to compare and evaluate performance in computer systems is so important. So in computer systems, performance is normally measured and is associated with time, how fast something gets done. That's probably what is associated with time is probably the most important way to assess performance in computer systems associated with time. But we can look at a specific metrics that have to do with time, because time can be counted in different ways. Okay, and it has to be clear. The whole point of spending time on this is that we have a methodology of assessing performance that is robust, because we are comparing apples to apples. We got to make sure that if we are comparing different things and assessing a value or a metric to them, that is applicable in the same way to all the things that we are comparing. So one of the things that we can measure is response time, and that could be very important for some computer systems. So the time needed to complete a task, including everything, okay? Memory accesses, disk accesses, I/O activities, the overhead of the operating system. Now, sophisticated processors are going to be doing work while it is waiting for some of these other things. Memory is much slower than the processor. Disk, since it is an electromechanical device and things mechanical and are much slower than electronic things, is going to basically, compared to the processor, whatever the disk does is going to take an eternity. I/O is all over the place depending on the I/O. Your keyboard and your mouse are really slow devices, but if you have a high-speed network connection, that may be very different. So it gets complicated if you lump everything together, mainly when you're just talking about how do I architect this processor chip. So we have to actually go in more detail than just looking at the response time, or what we would call the wall clock time, looking at how long a program is taking by watching the clock. That is not going to work. It has a lot of other things in there that it may convolute the data that we get. So that's what we would call the elapsed time or the wall time. What we really want to know is the CPU time, which is, and that's the name for it, CPU time, which is the time that the CPU spends executing, working on my specific job that I'm using to measure this performance across different architectures. Okay? So the system, the CPU time can be further divided between the user CPU time and the system CPU time, because the same CPU has to execute your program, but also the operating system is a program itself. It's not like it's running somewhere else. The same CPU is executing the supervisory operating system and your user program. Also, different programs are affected differently by the CPU and the system. So we got to make sure that we have a program or a collection of programs that is representative of the market or the application that the CPU is going to serve. That's very important. So let's say that, to be very precise, we are going to focus on CPU time, specifically to the processing of a specific task. Okay? And again, we can use representative programs, but later we're going to see how we can use a specific benchmarks that have been crafted to really focus on specific areas of performance of processors. So we can look at response time. That's one type of metric. So that is from the time that I tell the CPU, go and work on this specific problem or execute this specific program, and then it comes back after it finalizes. That is the response time. And that may be fine for a lot of applications. For example, if you are architecting a server farm for Google for doing searches, response time is important. So from the time that you click that, whatever you put and typed on that search box, you want something back. You want the results of the search served back as soon as possible. That is one application where response time is important. The other way to look at performance that is related to time is throughput, which is the number, is a completion rate of the task, rather than how much time a specific task takes. If the processor, while it's waiting on other things, it could overlap different tasks and get a higher completion rate of the task that is sort of independent of the actual time that it takes to do a single one. If we can get a higher completion rate of many tasks, that could be very useful. So something like scientific computation lends itself to that metric, where you actually want to set up your simulation, because let's say you're simulating something through time. So the completion of those simulations as you step through time, if you're running a very complex simulation in something like MATLAB, that is important. Throughput is more important than the completion of a single calculation at a specific time step. You want to finish the whole simulation, and then the throughput of those computations per time step become more important. So we're going to see, and we need to know, again, depending on the application, we need to see which is the best or the better metric. So let's start to define some simple relationships, simple arithmetic relationships. So this class doesn't have any, by far, doesn't have any type of complex math or anything like that, just simple arithmetic to define some relationships that are related to performance. And we're going to say that performance, we're going to define performance as the reciprocal, or 1 over the execution time. Now this execution time is going to be very specific. Is the time that the CPU takes to execute my program as I have defined it. Okay? So if I have two machines, I can set up a proportion or a ratio of performance of machine X divided by the performance of machine Y would be the execution time of my program as measured by the time that the CPU is spent on it, divide on machine Y divided by the execution time on machine X. And let's say that I come up with some type of number that is greater than 1, n. Let's say that is greater than 1. Okay? And if I just do that, and I have been very judicious on what I define as that program and how I measure the time, I can say with fairly good certainty that if n is greater than 1, that the performance of machine X is greater than the performance of machine Y. Specifically, I can also tell by how much as a percentage. So if that number is 1.2, I can say machine X is 20% higher performance than machine Y. And again, if I have defined clearly how I measure the time and the program that I measure the time on, that metric is very reliable. Okay? So why is time such a good indicator, or these metrics that are related to time? Why are they so reliable when it comes to being an indicator of performance? Well, these processors are digital systems. Okay, they are complex digital systems, and there are the circuitry in them. You have combinational type of logic, but you also have sequential type of logic. And you know from 312 that all sequential type of logic works in the basis of a clock. So it's like a heartbeat of the machine, the clock. And the clock rate is related to that CPU time, because the machine is doing its things on a clock by clock cycle basis. So, we can count the number of clock cycles that it takes to execute this program that I'm measuring the time for. And if I know the frequency of that clock, then I know the period, and if I know the number of cycles, I know the time. That's my CPU time. Okay? Now, as the processor is doing this, what it's doing is executing instructions. And in some architectures, it takes one clock cycle to perform one instruction. In some others, it takes many clock cycles. Normally depends on the instruction. Some instructions takes fewer clock cycles, some instructions take higher number of clock cycles. So one thing that I can define is an average number of clock cycles per instruction, or CPI. Okay? So clocks per instruction, and then if I have that average, the CPU time is going to be the clocks per instruction on average times the number of instructions times the clock rate. Let's take a look. So as I mentioned, that's just a review of CPU clocking. So I was saying that we wanted to relate CPU time and look at some relationships that have to do with the terminology that we just mentioned. So we can say that the CPU time is equal to the number of CPU clock cycles if I just count the number of cycles that it takes to execute that program that I'm using to measure the performance. And if I know the clock cycle time, which is 1 over the frequency of the clock, then I know what the CPU time is. Okay? So just looking at this simple relationship gives us a couple of insights. if performance is defined by having as small as possible CPU time, meaning that the CPU completed the task as fast as possible, I could improve the performance by reducing the number of clock cycles. So if I reduce the number of clock cycles, my CPU time, so if I reduce this term goes down. The other thing I could do is increase the clock rate. So if I increase the clock rate, the clock cycle time or the clock period will go down as well. So my CPU time will be decreased. So you will see, as we discuss implementations in the course later in chapter 4, how we have to trade this off. Okay? The clock rate against the cycle count, because I still need some time for something meaningful to happen. I can just not keep making the clock rate higher and higher or making the cycle time smaller and smaller, because these are actual physical circuits. There are capacitance involved in the connections. These are real transistors. These are electrons that have to propagate. So there needs to be time for these physical things to happen, although they can happen very fast. So I need to have, it's going to be finite. At the same time, if I don't have a meaningful chunk of time, a clock cycle that is meaningful for something to happen, then I have to break these instructions in many smaller steps, and it takes me a lot of clock cycles to complete an instruction to the point of diminishing returns, and the overhead that I have to add in circuitry to manage this multi-step operation may actually be detrimental to the architecture as I'm trying to come up with an optimal solution. So from a cost perspective. So we'll see how we trade off the clock rate. It's not just, and what I'm saying is that it's not just as simple as saying, just clock it as fast as you can. It's not that simple. You have to trade off clock rate versus the number of clock cycles, which means how much you have to break instructions into. So furthermore, the number of clock cycles is really the number of, as I mentioned, the number of clock cycles per instruction times the number of instructions. And there are two technologies that have to do with that, or a couple, but it's not as straightforward. You have the number of instructions, and then you have the number of clock cycles per instruction. So that one, that latter one, the number of clock per instruction, is a function of the architecture and the implementation, the organization of the processor as traded off against the clock rate. Okay, so we're going to see that. Then the other part, the number of instructions. The number of instructions also needs to be traded against the number of clock cycles per instruction, because let's say that you have a very complex instruction. An instruction does a lot of things in a single instruction. But if it takes you a lot of clock cycles to implement that instruction because it's very complex, then again, you counteract the benefit of having such a complex instruction. The other part in the number of instructions is the quality of the compiler, because somebody's going to be writing code at a high level or a high level language, but that code needs to be translated to machine code by a compiler. So the techniques that the compilers use to translate, to do that translation, to optimize for actual machine code or compiled code become very important to minimize the number of instructions, regardless. So that's the other part. Now, in this course, we're not going to be uh, talking about compiler design. So we're going to assume that that is there. We're going to be looking at mainly about the design of the instruction set architecture for a number of instructions that are not too simple but are not too complex, so they can be executed relatively fast with a relatively few clock cycles, and look at that trade-off against the number of clocks and the clock rate. And what we have seen through many years is that it really pays off to have simple instructions. So I can have a higher clock rate and fewer clocks per instruction than having very complex instructions. Even if having more complex instructions theoretically would reduce the number of instructions because I can do more with a single instruction, all that does really is reduce the size, the static size of the program. But normally, storage is inexpensive compared to the processor. So you'll see that that trend develop as we go through the course. So some further development of relationships of the things that I said. CPI for a program, function of the number of cycles for each instruction type. We'll see how different instruction types have different number of cycles because they can be grouped in that manner. Another thing, the frequency that each instruction is used in a program. That really is a job of the compiler. The compiler needs to understand the ISA, know which are the more complex instructions and the ones that are going to take the longer, and actually try to achieve the same translation from a high-level program using the number or the type of instruction that actually is going to yield an overall lower number of clock cycles. So obviously, from an architecture perspective, we have no, we don't control the frequency of each instruction in the program, but as we architect the instruction set, and as we organize and design the implementation, it is very, very important to understand what type of instructions would be conducive to or friendlier to a compiler so that we end up with a mix of instruction that minimizes that number of clock cycles. So it's all interrelated. You have to understand that part as well as an architect. So again, CPU time equals to the clocks, CPU clock cycles divided by the clock rate. Now this CPU clock cycles, okay, the number of clock cycles, as I mentioned, is the instruction count times the clocks per instruction, the CPI, for a specific for a specific instruction type. And then the same CPU time can be written this way, which is just recognizing that 1 over the clock rate is the clock period. Okay? So let's keep discussing these aspects. So the instruction count for the program, again, is determined by the program. Now, when we say determine that the program, of course, is determined by the algorithm, the quality of the algorithm by the programmer, the quality of the compiler, but also specific to this course, what we're going to be talking about is the ISA, the instruction set architecture, because that's what we are designing. We have no control on the compiler. We have no control on the program itself. But we control the ISA. Okay? Part of the ISA, when we design this, is the average cycle per instruction. That's determined by the CPU hardware. We're going to see that we're going to be discussing the implementation, the organization. So we're going to control the CPU hardware that we design. Okay? And then finally, if we have different mixes of instruction types with different CPI, that's going to be affected by the instruction mix. So how much of each instruction type is used in the program. Again, we don't totally control that, but what I'm saying is that it's very useful. I would say that is actually a requirement to have a good understanding of, as you design this ISA, and a big part of the ISA is the instruction, the actual instruction set, because instruction set architecture is that instruction set plus a number of other aspects. But the bulk of it is that instruction set. As you design that, you really have to have a good understanding of how that might translate into an instruction mix when somebody programs something that gets compiled by some compiler that you don't control neither of these two. So that's where we're going. Now, if we have different classes of instructions and the CPI is not constant, then the way that we take that into account is that the clock cycle is basically the sum of a specific CPI for a class of instruction times the number of instructions for that class. Okay? Then we can also, what that does is that we weight the overall CPI in our simple relationship, this one here, okay, our simple relationship, because remember, all we are after is CPU time, or trying to understand how we make this as small as possible. So we can abstract that CPI as the total number of clock cycles divided by the instruction count as a sum of the specific CPI for a class of instruction times the number of instructions divided by the instruction count. Sort of a relative frequency in the instruction set. So let me say that again. If I want the number of clock cycles and I have a real stream of a program running, I can actually watch the or if I can look at a program as it runs, and if I know the CPI for a specific instruction and I count the number of instructions for each specific set that get executed, if I do the sum, I can get the clock cycles. But let's say that I don't have that, and I'm just looking at the specific relative frequency of the instruction counts that are run for a specific type of instruction divided by the total number of instructions that get executed. I can apply that to a running program, but also I can just take a look at the mix of instructions in the ISA as it gets designed. If I don't have the benefit of having a running program or the data of a running program to actually look at a specific instruction counts for a specific instruction and count the total count of instructions, which would be the relative frequency. I can look at just the list of instructions and assume that the frequency or the probability of every instruction is the same, which is not totally true, but is an approximation. And then I can look at the static occurrence of instruction types in the instruction set and come up with some type of CPI where I can start doing some type of forecasting or assessment. Okay? So again, that may be so far the most confusing or trickiest concept that we have discussed so far. And again, if there are any questions, please chime in, and I can go through that again. So as you get the yes.
Can you just explain what the subscript I stands for? Is that for a program or specific instructions?
So this would be for a specific class of instruction. So let's say that we have arithmetic instructions is one class. And let's say that all arithmetic instructions take 4 cycles. So the CPI sub I for arithmetic would be 4. And if I count that I have 1,000 arithmetic instructions, that would be instruction count I. The instruction for arithmetic would be, for example, add, subtract, shifts, things like that. So it refers to a specific class or group of instructions that share the same clocks per instruction as architected. Now, that can be reduced to a point where every instruction may take a different clock cycle. So at that point, then CPI becomes the CPI for that instruction, and the instruction count becomes the instruction count of occurrence of that one instruction. Does that make sense? Did I answer your question satisfactorily?
Yeah, that makes a lot more sense now. Thank you.
Any other questions? This would be a good time. All right. So when you get the slides, on top of the homework that I'm going to assign, there are these problems in the slides. Okay. So what I want you to do is work out these problems, and if there are any questions, you come back and ask them in this forum. And if I need to work them here in real time, I'll do that. And if I want to work them offline and then show it to you, I'll do that as well. Okay. So there may be problems like this without answers. Some of them will have the answers, and we'll go through it in the slides. But when I give you the slides at the end of the presentation of the whole chapter, watch out for any problems that don't have answers and do them. But I think most of them should have answers, and we'll go through it here. Okay? So let's take a look at this one. Let's take a look at this one. Take a moment to read that. So our favorite program runs 10 seconds on computer A, and that has 2 gigahertz clock. And we're trying to help a computer designer build a machine B that will run this program in 6 seconds. The designer has determined that a substantial increase in the clock rate is possible, but this increase will affect the rest of the CPU design, causing machine B to require 1.2 times as many clock cycles as machine A for this program. What clock rate should we tell the designer to target? Okay, so what we know so far is that machine A takes 10 seconds to run a program with a clock rate of 2 gigahertz. Machine B, or we want machine B to take 6 seconds for that program, but that will make it so that the clock, the number of clock cycles is going to be 20% higher, because to get a higher frequency, which we don't know, which we are after, to get a higher frequency, the implementation is going to have to be changed in such a way that the CPI is going to change. Remember that we said that those were related and could be traded off against each other. Okay? So again, that sets it up, and work out things where you don't see the answer, and then come back if you have any questions. Another one. Suppose we have two implementations of the same instruction set. Okay. Now, once you hear things like this, same implementation of the same instruction set, what you should know is that if the instruction set doesn't change, okay, if the instruction set doesn't change, the number of instructions is not going to change because it's the same instruction set. You're not changing the only thing that the compiler could use to make a change. If you're not changing the instruction set, as far as the compiler is concerned, you haven't changed a thing. But you are changing some things here. Okay? But that's below the level of abstraction that the compiler sees. That's my light. So, and those are two different implementations. So we have machine A with a clock cycle of 250 picoseconds. Okay? So that would be 4 gigahertz. And has a CPI of 2 for some program. So the program is not changing. Okay? And machine B has a clock cycle of 500 picoseconds. So that would be 2 gigahertz with a CPI of 1.2 for the same program. Then a question might be, which machine is faster for this program and by how much? Okay? So, same instruction set, two implementations, clock cycle time, 250 picoseconds, 4 gigahertz, CPI 2. Machine B, clock cycle time, 500 picoseconds, 2 gigahertz, CPI 1.2 for the same program. Which one is faster? So these are the type of questions that you need to be thinking about. Okay?